Okay, so okay, so I remind you that we're in the middle of proving the following theorem, which concerns the solution to the Euler equation in two dimensions with concentrated vorticity. This has been the goal we've been working toward for a while, and so we've identified this this set of ODEs here. So here I have P is a vector, say an element of R2 to the M. So P has components P1 up to Pm, where each P sub j is a element in R2. So we have an object of this sort, a function of T, and it's all the system ODE. So each P sub little m evolves in this fashion. Okay, and then we assume that for times up to some T star, there are no collisions between separate PMs. Okay, and then the theorem we want to prove says that if we solve the Euler equations with vorticity, who is in some way close to these the initial positions for these PMs at time 0. So close means the support of the vorticity is concentrated around in epsilon balls around the initial positions of the ODEs. Okay, so the ODEs have this vortex strength gamma built into it, gamma sub j or gamma sub m. So if the amount of vorticity in the jth ball is gamma sub j, the amount corresponding to this constant up here, and if the vorticity doesn't change sign in any of these balls, then the theorem, which we want to prove, asserts that the vorticity remains concentrated around these balls. Initially, I assumed it was concentrated on a scale epsilon, and the theorem says that, well, it remains concentrated maybe on a larger scale, epsilon to the a, where a is some number less than a half. So these are balls a bit bigger than square root of epsilon. It remains concentrated, and so in particular, this really says that the vortex is following the trajectories given by solving this ODE. And the amount of vorticity in each ball remains as it was at the beginning. Okay, and so what we've done so far is we've said that this formally reduces to studying the Euler equations with background flows, or we'll recall this reduction. And so we studied this system of equations where we think of F as being a given background, and I remind you that this K, script K, is the recipe for recovering the velocity field U from the vorticity omega, the so-called Biot-Savart law, the Biot-Savart kernel we've seen in great depth. And so then P epsilon is the center of vorticity. This I is the second moment about the center of vorticity. So first we proved that we compared. So we imagine we have this system of equations with vorticity concentrated around some point P naught, so that the initial moment is of order epsilon squared. This is the scaling we're interested in. And so we proved then that the moment of vorticity around the center of mass remains of order epsilon squared in the setting we're interested in. And the distance of the center of vorticity, P epsilon, from something we get by solving ODE, P, is of order epsilon. And so here this is the ODE that just comes from the velocity field given by the background flow. Okay, this is one of the ingredients. That was a rather easy theorem, a very elegant and quick proof. Then the harder theorem was these bounds on the growth of the support of the vorticity. And so here we assume again the Euler equation with the background flow. We assume the initial vortex is concentrated in ball radius epsilon. And we assume there's some LP norm for some P bigger than 2, so that the growth of the vorticity is, like some negative power of epsilon. This is a very forgiving assumption. Okay, and then the conclusion is that the vorticity remains concentrated again on a somewhat bigger scale, on this epsilon to the A scale around the center of vorticity. And so this is just the definition of center of vorticity down here. Okay, and so with these ingredients, we'll finally prove the main theorem. We'll go back to the case of the whole Euler equations. And so here again is the main theorem, we have this system of ODEs, and we start with this concentrated data, and we want to show that the concentrated vorticity remains near the trajectories given by solving ODEs. Okay, and so let's see what we can do here. Oops, that's not what I want. So so let's give the proof, and okay, and so here it is. Right, and so the starting point is, as we remember, we write the Euler equations as a system. And so my initial vorticity is concentrated in these M blobs, and I just look at I look at the evolution of each of those blobs separately. And so I call each blob, I'll call omega sub epsilon and little m, and there'll be a capital M of those. Little m ranges from 1 up to capital M. Okay, so I wrote an equation for that. There are two pieces. There's the U epsilon m is the velocity field generated by the mth blob, and F epsilon m is the velocity field generated by all the other blobs. Okay, and so then in this way, I've taken the Euler equations and written it as a system of equations for these omega epsilon m's. So I've divided them in large pieces. Okay, and so so let's pause for a second, just to make sure we get this. And so again, here we're recovering the so this U epsilon m is the I apply the BO sub r kernel to omega epsilon m to find the associated velocity field, and then the F epsilon m is the velocity field generated via the BO sub r law by all of the other blobs of vorticity. Okay, and so this is the so I've written the equations as a system, and the good thing now is that if I look at this omega epsilon m, it satisfies the hypotheses in my earlier, or at least we'll see in a second that it satisfies the hypotheses in my earlier theorems, the ones about the background flow. In particular for this, so in this theorem we assumed a single blob of vorticity. That's for the initial data. That's what we have for omega epsilon m for each m. Okay, and so what we need, the main missing hypothesis is this: we assume that the background velocity field capital F was divergence free, which is the case for us because of the nature of the BO/SR law, and we assume that it was Lipschitz continuous, which is what we've just written down here. And so we need to find a constant L such that capital F epsilon m is Lipschitz continuous with constant L on the support of the mth vorticity blob at time t for every m and for every t. Okay, and so note, in the earlier theorems, we just assumed that this capital F was Lipschitz continuous everywhere. But that's stronger than we need. All I need is, this is only going to matter. The Lipschitz continuity will only matter on where omega is non-zero, where little omega is non-zero. So we only need Lipschitz continuity on the support of omega epsilon m, but we need this for every little m. Okay, and so to do this, I'd like to, so what I want to do, this is a kind of a common technique. I think in some parts of the math world, this is called a bootstrap argument, but somehow I never got used to that phrase. So I would call this a stopping time argument. And so I wanted to find some T epsilon, and basically this capital T epsilon is going to be the time up to which I'll be able to apply my earlier theorems, up to which this Lipschitz continuity hypothesis will be satisfied. And so how do I do that? Okay, so here's T epsilon. And so what I've asked is, let's draw a picture. So I start with, let me assume I have just two blobs to start with. I start with these points, so let me draw a picture for the ODE trajectories. I start with some initial centers of vorticity, and then they evolve, and then I evolve them following some ODE. So I get some P sub M of T. And first let's see, did I do this yet? Okay, I forgot to write something important. So I want to, let's see. So remember, capital T star is the time of a first collision. And so I fix some, I have to prove a conclusion that's valid for any T less than T star. And then I want to, and so if up to time T star if up to time capital T there's no collision, then I can find some delta greater than 0, such that all of the trajectories are at least a distance delta away from each other. Pm of T minus Pl of T is at least delta if okay, so for the ODE trajectories, I can always assume they stay some distance away from each other. Okay, so this distance is at least delta. And so then I put a ball of radius delta over 4 around each of these guys. And I know the distance between these two balls is at least delta over 2. And so if I consider any point in this in here, well, okay, so now let's go back and look at the assumption of the definition of T epsilon. So the definition of T epsilon is here. It's defined in such a way that essentially so up to time T epsilon, at any time up to time T epsilon, if I look at the mth blob will stay contained within this ball of radius delta over 4 around the mth ODE trajectory. That's the, and so I have these blobs, but they're, they stay close to the classical trajectories. Okay, and so in particular, that means they stay some distance away from each other. They stay at least distance delta over 2 away from each other. So I always have a distance delta over 2 between the different vortex plots. And okay, and so this is the definition of capital T epsilon. That the support of omega epsilon m at time t is contained in the ball of delta radius delta over 4 around pm at time. Sorry, this should be an S. Geez. Okay, so for every S between 0 and T, I have this containment of the support, and I take T epsilon to be the largest time interval on which this holds. Okay, and so then I want to argue that for times up to time capital T epsilon, I can apply my previous theorems that this crucial Lipschitz continuity assumption here is satisfied for some L who I can identify. So let's go on and do that. So my goal is to bound the Lipschitz constant. And sorry. Okay, and so I consider an X in the support of one of these blobs. And I consider time T less than this capital T epsilon. And I want to look at I want to compute the gradient of this background flow in the mth blob. And I have a formula for it. So I'm just writing down, so I write down the Bios of R, I write down the definition of capital F, and then I differentiate. And remember this K is X minus Y perp divided by X minus Y squared. So it's homogeneous of degree -1. When I differentiate K, I'll get something with homogeneous degree -2. And so this is what we're writing down now. I'll stop in a second to appreciate this. And so, okay, so the point is we can rather easily estimate this. Okay, so then, okay, so again, this is just the definition of f differentiated. This is k is homogeneous degree minus 1. Gradient of k is homogeneous degree minus 2. So it's bounded by a constant over x minus y squared. And x minus y is at least delta over 2. And so x minus y squared is most 4 delta to the minus 2, which is here. The point is that x is in the nth blob and y is in a different blob. And those points are bounded away from each other by the definition of T epsilon. And then this is just the sum of the gammas. I had some gamma j's at the beginning of their absolute values. And so I just call this L. This is some number. And it depends on the time capital T and so on. It depends on delta. But those are fixed. And we'll just call this the Lipschitz constant L. And so now I'm in a position to apply my previous theorems, the ones we reviewed a second ago, with this Lipschitz constant L. And so what do those give me? Those give me, so I have to introduce some notation to tell you, to state the conclusion of those theorems. But what they tell me is that the mth vortex blob remains concentrated on an epsilon scale around its center of vorticity. And so this little p epsilon m is exactly the center of vorticity of the mth epsilon blob. This capital I epsilon m is the second moment of the mth blob with respect to its center of vorticity. And then what I call capital P, I have 3 things I have to keep track of. Capital P is going to be the solution of the ODE, that approximately describes the motion of the mth vortex blob. And so remember, in my previous theorems, I compared the motion of this, for the background flow, I can compare the motion of the center vorticity to the particle trajectory given by solving the ODE associated with background flow, capital F. Here the relevant background flow is this F epsilon m. That's the background flow in the mth blob. And so I define capital P epsilon m to be the solution at ODE, the trajectory given by that particular flow. And I take it at time 0 to be the center of vorticity of the mth blob. Okay, and so then I want to apply the previous theorems with a number b. So those are valid for any power of epsilon less than epsilon to the 1/2. And so I fixed them. So the statement of the theorem had an A, and I wanted to prove things are contained in a ball with epsilon at the A. Here it's convenient to work with a slightly smaller ball to give myself some room for later on. So I take a B who's bigger than A, between A and 1/2, and I'll apply my previous theorems with B, with epsilon to the B. Okay, and so here's what the theorems say. They say the second moment around the center of vorticity remains of order epsilon squared. They say that they give us a bound on the distance between the center of vorticity of the mth blob and the trajectory given by the background flow in the mth blob with this parameter set epsilon. And finally, they tell us that the mth blob is contained in a ball of radius epsilon to the b around its center of vorticity. Okay, and so by combining these, this one and that one, the support is near the center of vorticity. The center of vorticity is near this capital P who solves the ODE. And so my conclusion is that the support is contained in a ball around the trajectory given by solving the ODE. Here, if I add this epsilon to the beta here and this C epsilon here, I'll find that this, by the triangle inequality, the support is contained in the distance from any point in support to here will be the distance from the point of support to P epsilon m plus the distance from here to there. And so it's epsilon to the b plus C epsilon. If epsilon is small enough, this C epsilon is smaller than epsilon to the b, and I can write that as just 2 epsilon to the b. Okay, so really this is epsilon to the b plus C epsilon for epsilon. Small. Okay, good. And so now what I need to do is right, so I have 3, let's draw a picture of the mth ball. So I have this mth ball, and I have this Pm at time t. This is all taking place in the ball of radius delta over 4, I think. And then I have a capital P epsilon m at time t. And so this is, so these two things solve somewhat different ODEs. And then I have a little p epsilon m at time t, the center of vorticity. And so let's again make this be purple. And so I know that this center of vorticity, and indeed the whole support, is close to this capital P. But I still need to say that the support of vorticity remains within the ball of radius. Remember, the stopping time delta, this T epsilon, is the first time at which the support leaves a ball of radius delta over 4 around this P sub m. So I have to compare, I need to compare this little p sub m of t and the capital P epsilon m of t. These solve slightly different ODEs. Okay, and so little p sub m of t solves an ODE where the right-hand side is what I'll call f sub m, which is what I'm writing down here. This is just the right-hand side of the point vortex ODE system. And whereas this, well, I'll write it down in a second. So I'm going to just look at the, what I'm writing down here is the difference between the right-hand sides of the ODEs for this capital P epsilon and the little p, the capital P epsilon m, and little p sub m. Okay, and so so here's the claim. So the point is, this P sub m, this guy, so this solves the point vortex ODEs. There are a bunch of points. Each one generates a flow, and each one gets convected by the flow generated by its neighbors. This little p epsilon, this capital, that's this guy. This guy is convected by the background flow generated by the blobs. And the argument is that as long as these blobs are close to the points where they're supposed to be, then the background flow experienced over here will be close to the one generated by the points. So that's what we have to estimate. And so I just write down so the background flow generated by the blobs is by definition what I get if I ignore the, well, it's these terms. This by definition is the background flow. I look at the velocity field generated by the other blobs. I add those up. And then for each m, if I write this down, well, the point is that the integral of omega epsilon L is always equal to gamma sub L. And so I can replace this by this integral. And I see that this is the thing that characterizes the difference between the two ODEs that I'm interested in. Okay, and so I just want to see if this is small. And so my situation is I'm considering a point x in over here someplace in this in the purple region, actually in the support of the mth blob, and I consider a point y who's in the support of a different blob. And so I know they're kind of far away from each other. And what I want to argue is that if the other blobs are close to where they should be, then the velocity field, capital F epsilon m, is close to, the background flow is close to what it should be. Okay, and so I consider x in one blob, a y in a different blob. And I know these are dotted away from each other again. And so I can say, well, and I want to compare the integrand here. I'm looking at this difference. And so the point is that y and p epsilon at time t are kind of close to each other. And they're both kind of far from x. And so I just apply I apply calculus, the mean value theorem, if you like, to this function. And here's what I find. That k of x minus y, so again, k is the bios of our kernel, minus k at x minus p, will be k at x minus z for a point z in the segment between y and p. Okay. And okay, so again, it's y minus p times the gradient of k at a point on the segment k at x minus z for z on the segment between y and p. And again, because x is over here and the segment is contained in the ball of radius delta over 4 around a different point. So this is z wherever it is at least a distance delta over 2 from x. And again, this gradient of k is scales like distance to the minus 2. And so this thing will be of order delta to the minus 2 with some, and I can compute the constants explicitly if I wish. And so from this gradient term, I get a delta to the minus 2, and then I just recopy the other term. And then let's see, what do we know? We know that something is missing. There's a missing subscript. Let's just, there it is. I know that every point in the support of the ELF blob is close to the ELF capital P, and so we already have this estimate from above that y minus capital P is of order 2 epsilon of the B. Okay, and so then the conclusion is that if I combine, I have this expression up here for the difference of the background field in PDE and the point vortex ODE, and that involves this integrand. If I insert this into here, then I will get the following estimate for the difference between the background flow in the mth blob and the function given by the point vortex ODEs. Okay, and so I want to, so I get a, well, okay, so then let me just write this down. And so the reason I was interested in this is exactly because I want to control the rate at which the trajectory given by the background flow diverges from the trajectory given by the point vortex ODEs. Okay, so that's exactly what we're writing down here. And so now I'm summing over all the blobs. I look at the difference between the point vortex ODE trajectory and the background flow trajectory. And okay, I can just by sort of easy calculus considerations, I can bring the time derivative inside the. I just use the chain rule. I just do some easy estimates, and then here I'm using the ODE. So by definition, these are the ODEs that define these trajectories, capital P and capital and little p. Okay, and then finally I use this fact here, and I get this estimate. Okay, so the picture is again, if every blob is close to where it should be, then the vorticity generated by the blobs is close to the vorticity generated by the points, or sorry, the velocity field, the generated by the blobs. Okay, and so then what I can do, if I wish, is I can I can modify this a bit. I'm just going to add a constant. That doesn't change anything. Okay, and so then I have exactly the same thing on the left-hand side. I can call this some f of t, and this says that df dt is bounded by a constant times f of t. And so then I can just integrate that. and find that f of t is less than e to the ct. Oh, okay, I should say at this point up here, so here I was indicating the dependence of the constant on delta. And then I said, well, whatever, delta is just fixed. Once I fix time capital T, I fix the delta, and so I'll just call it C. And so here I remember that C depends on delta. And down here, I forgot even that. I'm just calling it constant C. But anyway, it's something we could compute in principle. Okay, and anyway, this has the form df dt is bound by ct, and so our conclusion is that f of t is less than f naught times e to the ct. F naught is, I can see if I look at this at time 0, that's e to the, it's 2 e to the b. And so then my conclusion is that the difference between the point vortex trajectories and the trajectories given by the background flows has this growth, like some power of epsilon. And again, I'm looking at a fixed time interval, and so this e to the ct may get huge, but it's just fixed. Okay, and so then, and then we've already, we've already shown that that the support is contained in a ball around these capital P's, a ball of order epsilon to the b, it was 2 epsilon to the b. And then in turn, the capital P's are close to little p's on this epsilon to the b scale. I don't know what happened to this. And so then the support is also contained in a ball of radius of order epsilon to the b around the trajectories given by the point vortex ODs. And then and my assumption was that all of this, oops, what did I do? Well, my assumption was that all of this, I think I'm done with this, that all of this is valid up to this time capital T epsilon, which is as long as the trajectories stay within ball area delta over 4 around the center piece of M. But what this says is that, you know, for times up to time capital T epsilon, as long as they stay within a ball radius delta over 4, in fact, they stay within a ball radius. So okay, so here I'm tacitly choosing epsilon small. Okay, so A is less than B. So A is bigger than B, excuse me. No, sorry, A is less than B. So I can do this. And then if epsilon is small, then and this is true also. And so actually, let's make this be delta over 8. Okay, and so what we've shown is that as long as the blobs are contained within balls of radius delta over 4 around these point vortex trajectories, then in fact they are contained within balls of radius delta over 8 around the point vortex trajectories. And this will be valid for, and so we see that we can never reach this time capital T epsilon. I mean, actually we put an upper bound on T epsilon. We assume in the definition it's no bigger than this T, but this implies that that capital T epsilon is greater than or equal to the T we set at time 0, hence equal to T, since by definition it was the other inequality held. And so then what have we shown? We've shown that up to the whole time capital T we fixed at the beginning, in fact we have these containments, and that proves the theorem. But the whole, and so okay, we had to mess around to get some details right. But the whole point is really contained in this picture, which is that once I know that the blobs are contained away from each other, then I can apply the earlier theorems. And once I know they're bounded away from each other, I can apply the earlier theorems. And then I just have to mess around a little bit to make sure that the background flow is close to the point vortex ODE flow. Okay. Any questions? So anyway, that finishes the proof of this theorem. Beautiful theorem. And again, due to Marchioro and Polverenti in the first steps were in mid-80s, mid-90s with refinements by Marchioro and Caprini, for example, Marchioro and Buddha in the last few years even. And refinements, in fact, also by Christian Zeiss, who remarked that that it suffices to assume this LP bounds rather than L infinity bounds for the vorticity. Okay, and so let me then, I want to discuss a variant of this. And here's the variant. So the variant is, what do I want to do in a bounded domain? So here's, so let's draw a domain D. Let's make it more dignified color. So here's a D in R2. Let's say it's bounded, connected, simply connected, and with a smooth boundary. Connected, if it's not connected, I just consider each piece separately. Simply connected, we'll see the role of that in a second. And so I want to mimic the same, I want to basically do the same proof on it. And we'll see we can pretty much use the results we've developed to give a very quick proof. And remember, when we study order equations on a bounded domain, we always have the boundary condition. You may, I mentioned this once like a month ago, so you may have forgotten. But on a boundary domain, the natural boundary condition is just to assume that the velocity field is tangential along the boundary. So the normal component of velocity vanishes on the boundary here. Nu is the outer unit normal. And then, and so a huge role in the previous proof was played by the Biot-Savart law, which told us how to recover a velocity field U given, once we're given a vorticity omega. Let's ask, how do we do that in this setting? And so I'll just do it. Well, so what we did before is we'll look for, we'll say U is the so again, grad perp is, I think, minus D2, D1. Okay, and this was our recipe before. We said we invert the Laplacian to get some function we call psi, a stream function. And then we took U to be the orthogonal gradient with a minus sign, I believe. And then, this vanishes is just by, there's some kind of, this is a difference of mixed partial derivatives. And okay, so then these conditions hold. But what do we? But in order to get the boundary condition to hold, let's say that. Let me erase this because we only. Well, okay. Okay, so let's say that. I want to have this. I also need, the point is I also need boundary conditions for psi. And let's say psi is 0 on the boundary of the domain D. Okay, and so so my claim is that this is a good thing to do because it will arrange, it will guarantee that this condition holds. So then U dot nu is minus grad perp psi dot nu, that's minus D2 psi D1 psi times nu1 nu2, the dot product. And I can just, and so I can see this is grad psi dot nu perp. The point is that if I take the unit normal and rotate by 90 degrees, this is the tangential derivative of psi, which is 0 because psi is constant on the boundary. So if I so as I move along the boundary, it doesn't change. The tangent order vanishes. Okay, and so I can see that this boundary condition for psi will arrange the proper boundary condition for u. Okay, and so using this, I want to write down an analog of the Biot-Savart formula on a bounded domain, a smooth boundary with these boundary conditions. And here, I guess I'll just write it down. Here it is. So what I have to, and so what I would do is I would find a, so I'll do what I did before. I would find a formula for this psi, and I know how to solve this equation on all of R2. And what I have to do is I have to modify that solution so that it has the right boundary values on the boundary of the domain. And there's a kind of a standard way of doing this. And so, sorry, so I can write down a formula for psi in this way, and then I take the orthogonal gradient, and that will give me u. And so for psi, what do? I'll take the, I'll convolve with the logarithm as before, and that will give me a function whose Laplacian is omega. And then I want to add on a harmonic function that's not going to change the Laplacian, but it'll cancel out the unfavorable the non-zero boundary conditions. And so that's this function h of x and y. And so, okay, going over this a bit quickly, but well, so let's see, maybe I should say a bit more about this. Let's see, I think I want a minus h of x, y, omega of y, dy. And so I claim that this will for h defined below, we'll look at it in a second. This will have the right property. It'll be a function whose Laplacian psi is equal to omega, and it will equal 0 on the boundary of the domain. This thing over d, and then I find u by taking the orthogonal gradient of that thing. That's exactly what k is here. K is the orthogonal gradient of this kernel. Okay, so let me see. Okay, what's the point? So the point is, if I temporarily ignore the h of xy term, we know that the Laplacian of that thing is equal to omega. Okay, and so that was one of the conditions I wanted for psi. Now let's so now I want to add on something who will preserve that, preserve the Laplacian, but change the boundary conditions. And so I add on an h, and so I want to be able to take the Laplacian in the x variables, and still get and I want so now let's focus on this piece, the h piece. I want the Laplacian of this thing to be 0, and so that'll happen if the Laplacian in the x variables of this is equal to 0. Then I can differentiate the integral sign. That's all cool. And I want and I also want the boundary values to equal 0. So I want to know that if x is in the boundary, then I'd like this to vanish. And so for that, I just need, for every y I need, so note this, by the definition of psi, this equals 0 if x is in the boundary of D. Okay, and so what I've done is I've just modified the kernel valid on all of R2. I've modified it in a certain way so that I get so that this function psi will solve the right equation and have the right boundary conditions. And then I take the orthogonal gradient of that. I call that k of x, y, and this is my new Biot-Savart law. Okay, and so then if I want to study vortex dynamics in this bounded domain, well, here's my claim. let's draw a domain with two vortices in it. And okay, so if I look at well, okay, so the velocity field of a sum of gamma L delta P L is, well, it's the sum of these K of X P L times gamma L. So this K of XP is exactly the velocity field generated by a unit of vorticity at the point P. And then each of these Ks has two pieces. There's a X minus PL perp over this thing squared. And then there's a H of X or grad perp of H of X and PL. Okay, and so then if I ask what's going on at the mth, at one of these points, what's going to feel? Well, there's one singular piece. There's the piece that it generates itself. It diverges like a distance to -2, and then there are the contributions. There are these contributions from all the other vortices, and then there are these contributions from all the other vortices. But then you see the point is. If I look at the contribution from the L, if I call this PL, if I look at the part here generated by PL, at the point PL, it's perfectly smooth. And so we saw that the singular part, okay, it's singular, but it doesn't, we saw before, it doesn't affect the dynamics of the point itself. This is non-singular, but there's no reason it should leave the point smooth. It should leave it immobile. And so then right, so what we do here is, well, we say that we'll predict that the law of motion is this. We look at all the velocity fields generated by all the, and I should call this M, but at the mth vortex, I look at the velocity fields taking into account the boundary conditions generated by all the other vortices. But then there's also a contribution from the non-singular part of the velocity field generated by the mth vortex itself. Okay, so even if there's only one vortex, then the presence of the boundary will in general cause it to move. The interaction of the boundary will cause it to move, even if there's only one piece. Okay, this is the predicted law of motion. And let's see, so there's a theorem, which is a precise analog of the previous theorem okay, so I consider the Euler equations on the domain with the boundary condition. So this is the new element, and I'm in the domain. And then I replace the ODE from before by this modified system of ODEs, which I've just given a very crude heuristic argument for, which is that we look at the flow generated by everyone, and we say the part who's singular but purely rotational around any vortex isn't going to move anywhere, and so we can ignore that. And this has been justified in our previous result. Okay, so in fact, the proof is just a simple modification of the earlier theorem. And maybe I'll go over that in a few minutes at the beginning of the hour on Thursday. And then I've decided what I'm going to do next, contrary to what I said earlier, is I'd like to talk about, here's the starting point. I'd like to talk about this. So 3D Euler with cylindrical symmetry. And so this is connected to the, this is an open problem, if you like. Just to get a good mathematical explanation of this thing we see in these videos. And so, and then I said earlier we would do the gross Pittias equation. We'll turn to that a bit later. I should say this is an open problem for Euler. But it's a theorem for the gross Pittias. A theorem that's too technical to discuss in this class, but we'll see that in another week or two, we can basically get to the frontier of research on concerning this Euler question. I can tell you everything that's known, pretty much. And we'll see why it's harder than the point vortex question. Okay, that's it for today. And that's it for me. As usual, if there are any questions, it would be great to hear them. And right, so welcome questions. Okay, Lars, hi.
Yeah, hi. I would have one. Is it known what happens when you consider a non-simply connected domain? So say you have an obstacle in your domain and you prescribe some circulation around it.
Yeah, I forgot to mention this. So the reason I wanted simply connected is here when I do this, if I'm solving this system of equations for if I'm given omega and I'm solving for u, there'll be a unique solution on a simply connected domain. But if the domain is not simply connected, then the solution is non-unique. Let's recall this. So, for example, if I consider the homogeneous equation on a non-simply connected domain, for example, on an annulus, I could have u to be the gradient of the angle function theta, would be x perp over r squared. This function satisfies this system, but it's not the gradient of anything. Right, this function is a non-zero solution to the system. Okay, and so so on non-simply connected domains we can solve for the velocity field, but the vorticity doesn't uniquely determine the velocity field. What's going to happen? I mean, yeah, that's understood. So
you could prescribe the circulation, no? That would be
that's the circulation, yeah. And so you can sort of decouple the velocity field into two pieces. One would be say this piece, and that just sits there, doesn't change. And then the other piece is the piece generated by the vorticity. And so, for example, in this setting, if I have some vortices and I have this background flow, well, it's going to tend to convect to move everything around in a circle. And so it just is a kind of a technical headache.
Okay.
But it's not fundamentally any different.
Okay, I see.
Anyway, that's the reason that the simply connected assumption is very convenient. Yes.
And then I would have another question. Probably you said it last time. Is this factor 1/2 for the exponent of the radius of the ball? So it's always alpha. It's always epsilon to the a with an a that's smaller than 1/2.
Yeah.
Is this like? Is this where does this 1/2 come from? Is the estimate like say optimal?
We had some estimates, right? So the main, in some way, the main point was this thing that says if we solve the Euler equations with the background flow, and we start with the ball radius epsilon, and then we wait a while, and we can guarantee that it will be contained within the ball radius of this epsilon for alpha bigger than 1/2. And so the point was we computed dt of. We looked at the flux of vorticity. Through some, essentially we looked at something like this. And so what is this? This was this function chi looked like this. And so we're looking at essentially the amount of vorticity outside a ball radius r, how that changes. And so that's the amount of vorticity flowing through the region here. The flux through this region where we go from 0 to 1. Okay, and so when we did this, there were some, and so there was a r and a r plus h, I believe, and there were some things involving, this I epsilon, et cetera, But in one of these things, there was an r squared h squared, and then we took h equal to r. So we said this was 2r, and this was then r to the 4th. And this, on the other hand, was order epsilon squared. And so somehow, if r is bigger than, if r is smaller than square root of epsilon, then everything goes to hell. And as long as r is a bit bigger, then things are okay. And presumably that's technical. I mean, what this lemma suggests is that I mean, all I can tell you is that for any, we start on the ball radius epsilon, and for any positive time, the best you can say is epsilon to 1/2 or a bit bigger. So it sort of is, the lemma is consistent with the unbelievable scenario of instant expansion, this epsilon to 1/2 size. But that's the best proof there is.
Okay, thank you.
You're welcome.